Hello there, this is chapter 1.1 and we will be talking about bonding and structure. The first video will recap chemical bonds, in particular ionic and covalent bonds. The second video will look at electronegativity. The third will look at the representations of molecules, whilst the last video will be concerned with constitutional isomers. This slide is related to solo taxonomy in that by asking these questions we can begin to see your mastery of a concept that you've already covered in Modern Chem 1. So if you're able to tell me what are the types of bonds that can form, then this is probably operating at a uni-structural level as you're identifying things. Whereas if you can describe how those bonds are formed, then you might have a number of ideas that aren't necessarily related to each other, and so as you list those, this forms part of your multi-structural stage of understanding. Whereas when you use electronegativity to begin to relate this to explaining why and how bonds might be formed, then that's different, and we're now at the relational stage. And finally, when you use electronegativity to rationalize other phenomena beyond bonding, then this is known as the extended abstract, and it's where we hope you'll be by the end of this lesson.
Let's have a recap of some chemical bonding. So the two main types of chemical bonds that we will concern ourselves with are covalent bonds and ionic bonds. So let's have a little think about how those bonds are formed. Well, covalent bonds are formed by the sharing of electrons between two or more atoms, and these bonds typically occur between nonmetals or between two of the same or similar elements. So two atoms with a similar electronegativity won't exchange an electron from their outermost shell. Rather, the atoms share those electrons such that their valence electron shell is filled. So such examples of this might include methane, carbon monoxide, and hydrogen. Now, ionic compounds, on the other hand, the atoms that are involved typically have a large difference in electronegativity, and this large difference leads to the loss of an electron from the less electronegative atom, in this case sodium, and the gain of that electron by the more electronegative atom, and this results in two ions, in this case a sodium cation and a chlorine anion. And it's these oppositely charged ions that fill an electrostatic force of attraction, and this electrostatic attraction is what constitutes the ionic bond. Now, as I mentioned before, why do atoms want to do this? Typically, it's so that they can achieve the noble gas configuration. And for the main group elements, there's a rule of thumb observation called the octet rule. And the octet rule says that the elements tend to bond in such a way that each atom has 8 electrons in its valence shell, giving it the same electronic configuration as a noble gas. Now, hydrogen and helium are exceptions to the octet rule because they are in period 1, and those elements in period 1 can have no more than 2 electrons in their valence shell. Now, the octet rule is a chemical rule of thumb that reflects an observation that main group elements, that's those in group 2, tend to bond in such a way that each atom has 8 electrons in its valence shell, giving it the same electronic configuration as neon. Now, the rule is especially applicable to carbon, nitrogen, oxygen, and halogens, but it is also applicable to the metals sodium or magnesium. This slide is a case in point of the octet rule. If you look at carbon, the 1s2 electrons are part of the inner shell, and so these don't bond. However, the 2s2 and 2p2 are carbon's valence electrons. Carbon is in group 4. So it uses its 4 valence electrons and 4 other electrons to form 4 shared pairs of electrons. These 4 shared pairs of electrons become isoelectronic with neon, that is, they have 8 electrons in their outermost shell. Nitrogen does exactly the same thing. Nitrogen has 5 electrons in its valence shell, and so therefore only needs 3 bonds in order for it to become an octet, whereas oxygen starts with 6 valence electrons and so therefore only forms 2 bonds.
There are 2 questions that we're going to consider on this slide. First is whether this is a valid molecule, and we'll talk about this by discussing each of the atoms involved. The second is whether or not all of those electrons are shared equally. Now, for hydrogen, each of those hydrogen atoms obey the duet rule. There is no hydrogen atom there with any more than 2 electrons around its atom. Now for carbon, that carbon has 3 bonds to a hydrogen as indicated by the red dots and 1 bond to the nitrogen as indicated by the blue dot. All of those are shared pairs of electrons. Carbon started off with 4 valence electrons and so therefore has an octet. When we look at nitrogen, this is the same for nitrogen. It too has an octet. Remember, nitrogen has 5 valence electrons and it will form 3 bonds. So one of the bonds is to carbon, one of the bonds is to hydrogen, and one of those bonds is to oxygen. And finally, oxygen is the same story. So the oxygen has 6 valence electrons. There are 6 black dots representing those valence electrons, and 1 red dot represents the electron pair being shared with the hydrogen, and 1 blue dot represents a shared pair of electrons with the nitrogen. So therefore, every atom within this molecule satisfies either the duet or the octet rule. However, this does not mean that all of the electrons are being shared equally because of differences in electronegativity. So the electron density around each atom is different, and we'll talk about this in the later half of the lecture.
There are 3 exceptions to the octet rule. The first concerns molecules with odd numbers of electrons. So, for example, nitric oxide has nitrogen and oxygen bound together. Now the nitrogen contains 5 valence electrons, whilst the oxygen contains 6. So there is no possible way for all of the atoms in such a molecule to satisfy the octet rule. And so I'm going to ask you please to draw the Lewis structure of nitric oxide. Now, in addition, you can also have incomplete octets. So in some compounds, the number of electrons surrounding the central atom in a stable molecule will be fewer than 8. Now, beryllium is an alkaline earth metal, and so you might expect it to form ionic bonds. But because it's very small size and it's quite high ionization energy compared to other metals, this leads to beryllium forming typically molecular compounds. So beryllium only has 2 valence electrons. It typically does not attain an octet through the sharing of electrons. Boron and aluminium have both 3 valence electrons, and these also tend to form covalent bonds with an incomplete octet. The central atom in the borane molecule has 6 valence electrons, and this is the second Lewis structure that I'm going to ask you to draw. Finally, the elements belonging to the 3rd row and up, so the sulfur of the sulfite anion, have what is called an expanded octet. Now the atoms of the second period cannot have more than 8 valence electrons, However, the atoms of the third period and beyond are capable of exceeding the octet rule by having more than 8 electrons around the central atom. So, starting with the third period, the D sublevel becomes available, so it's possible to use these orbitals in bonding, and this results in an expanded octet. Now, for the expanded octet, I'm going to ask you, please, to draw the structure of phosphorus pentachloride. And once you've done that, you can resume to the next video after you've checked your answers at the website at the bottom of the page.
In this video, we're going to be discussing electronegativity. Now, what is that? Well, electronegativity is the ability of a bonded atom to attract the electrons in that bond towards itself. And there are two key takeaways from this slide. When we look at the Pauling scale of electronegativity, which we see in table 1.1 for some of the elements, we notice that the electronegativity of the elements increases from group 1 to group 7 across the periodic table. Also, the electronegativity values increase up each group of the elements as the atomic number decreases. Now, there have been many attempts to put some numerical values on electronegativity, but the Pauling scale is the one that we're going to use. Now, why is this important? Well, these electronegativities can be used to calculate a difference between the bonded pairs of atoms. And what it does is it introduces a degree of polarity in covalent bonds between different atoms. So, for example, if you have a bond between, say, lithium and fluorine, then what we'll appreciate is that there is a very large difference in the electronegativity value of these two elements. And why is that? Well, lithium is a metal, so it's more likely to not want to hold on to the electrons, but rather to give them away, whereas fluorine, being the most electronegative element, is more likely to want to hold on to the electrons than what lithium is. Now, this is an important concept for chemical bonding, as the way of understanding polar bonds and also molecular dipole moments is very useful in understanding physical properties. The other thing that this is useful for is for thinking about trends in acidity, which we'll be talking about more in chapter 3. And then we'll also be using polar bonds to explain sites of electrophilicity and also to describe nucleophilic behavior in reaction mechanisms later in this course. But then let's think about what a covalent polar bond looks like, and we'll talk about this on the next slide. On this slide, we're going to consider the polar covalent bonds that exist between hydrogen and chlorine in hydrogen chloride. Now, there are two bonding models presented. The first is correct in that this is a covalent bond. However, when we have a symmetrical distribution of electron density around the atoms, what that suggests defies what we've just been talking about, that the chlorine would have less of a pull on hydrogen's electrons, or we would say that hydrogen here has the same pull on chlorine's electrons. Now, that doesn't make sense, so that doesn't truly represent the model. In addition, though, we also have an ionic bonding model presented on the right-hand side. Now, this is also not the case because there is a covalent bond between hydrogen and chlorine, so therefore the electrons are being shared. So the truth lies somewhere between these two models, and we'll talk about this on the next two slides. On this slide, what we're going to consider is the actual bonding model that we use for hydrogen chloride. And what it tells us is how the electron density is distributed between the two atoms. But before we do that, let's think about a non-polar bond. Now, I want you to imagine in your mind's eye that it could be either hydrogen atoms, so two hydrogen atoms to form a hydrogen molecule are approaching each other,
Or you could say two chlorine atoms are approaching each other to form a chlorine molecule. So as I play the video on the right, these two atoms approach each other, and the nuclei of each atom has an attraction for the electrons of the other atom. But they're going to be the same. And the reason that that attraction is going to be the same is because each of those atoms will have the same pull on the other atom's electrons. And so in a nonpolar bond, the electrons are shared pretty much evenly between those two atoms, and the electron density then is greatest between those two atoms. However, you can observe that for hydrogen chloride, we have like a teardrop shape. And what that teardrop shape represents is that most of the electron density has been shifted towards the chlorine atom. And that makes sense because chlorine has a greater electronegativity than hydrogen. So let's play the video and see what happens when hydrogen and chlorine approach each other. So when the hydrogen and chlorine approach each other, what you saw is that the electron density shifted from the hydrogen towards the chlorine. And the electrons are still on average found between those two atoms, but rather they are being shared in an asymmetric fashion. Now, because there hasn't been a complete electron transfer, then what we use to represent this is something called a partial charge. Now, the partial charges are shown at the bottom of the slide, and the delta plus represents that the hydrogen has less of the electron density, and the delta minus represents that the chlorine has a greater electron density surrounding its atom. The arrow underneath represents a bond dipole, and we also draw these in such a way that the arrowhead is always placed closest to the atom with the greatest electron density. Now, is there a way of predicting how polar covalent bonds are? Yes, there is. And on the next slide, we're going to use the differences in electronegativity to actually ascertain this information. On this slide, we're going to use Pauling's scale of electronegativity to calculate the electronegativity differences between two atoms in a bond. Now, in the first row of the table, bonds that are considered as ionic typically have electronegativity differences that are greater than 1.7. And another thing to consider is that these are atoms that are a non-metal bonded to a metal. In the second row, we have a polar covalent bond type whereby there will be an electronegativity difference of 0.5 up to 1.7. And typically, these will contain atoms in a bond where both of those atoms are non-metals. Finally, in row 3, you'll see that non-polar bonds are ones that have electronegativity differences of anywhere between 0, i.e. the atoms are the same, and up to 0.4. Now, there isn't enough of an electronegativity difference between these two atoms in order to have a polar bond. What I'm going to get you to do is for each of the bonds presented here is to pause the video and to calculate the electronegativity differences. So resume the video when you're ready to continue. So the first example is sodium chloride, and what you would do is you look up the most electronegative element first of those two atoms, which is chlorine. Chlorine has an electronegativity value of 3, and then you subtract sodium, which is 0.9, and this gives an electronegativity difference that is 2.1. Seeing as this is greater than 1.7, this is indeed an ionic compound. Now, for the next row, we have methanol, and we're interested in the oxygen-hydrogen bond. Oxygen is the more electronegative element, so it has an electronegativity value of 3.5, and when we take away 2.1, we get an electronegativity difference of 1.4. Let's do the same thing for hydrogen chloride. Chlorine is 3, hydrogen is 2.1, and so we have 0.9. Now, finally, if we look at one of the bonds in methane, we're just looking at the difference between the carbon-hydrogen bond. Carbon has an electronegativity value of 2.5, whereas hydrogen is 2.1. Now, this gives a difference of 0.4, and so we cannot use partial charges to represent a polar bond, because there is no polar bond. And obviously hydrogen, if you have two atoms that are the same, then when you take those values away from each other, you get 0. On this slide, we're going to think about relating and extending our knowledge, which is something we said we would do in the last video. So we've considered electronegativity, bond polarity, and the question being asked is, why is hydrogen iodide considerably more acidic than the other hydrogen halides? Now, you may be feeling some discomfort to this question because you may have predicted that hydrogen fluoride is considerably more acidic, and that would most likely be based upon just looking at the electronegativity differences. However, we need to consider the other data as well to make sense of this. So let us think about that now. Now, how do we get this to be an acid? Well, the hydrogen fluoride, hydrogen chloride, hydrogen bromide, and hydrogen iodide need to break their bond to produce H+ ions and the halide ion. So when they're placed into water, the oxygen atom of the water pulls on the proton, and this provides enough energy to overcome the bond that exists between each of these hydrogen halides. Now, if we look at fluorine and hydrogen have pretty similar sized atoms, and although there is the biggest electronegativity difference between these two atoms, there's also the shortest bond. And that really shows the great degree of attraction each atom has for each other, and therefore more energy is going to be required to break this bond, to dissociate it, to form H+ ions. Whereas if we look at hydrogen iodide, conversely, this has the largest bond, and that makes sense in terms of electronegativity, because if we consider the iodine atom, the iodine being larger, there is more shielding, and so therefore iodine has less of a tendency to attract the bonding pair of electrons than what, say, fluorine does. And so therefore less energy is required to break this bond, and because less energy is required to break this bond, then this is the more acidic compounds in this series. In this video, we're going to be looking at the different representations of organic molecules, and to start us off gently, we're going to be talking about just hexane. Now, hexane's molecular formula we see is C6H14. Now, this does not provide us with any information in a two-dimensional or three-dimensional way about how these atoms are bonded to each other. The first way in which we can see this in a two-dimensional format is through the most commonly used Lewis structures that up till now you've been familiar with. So we call this the displayed dash formula. However, for increasing numbers of carbons, this becomes a bit of a pain to draw, and there's a better way of doing this, which I'll tell you about later. The first three-dimensional way of representing hexane is shown as the ball and stick representation, and this represents your own model kit, which I hope you have. The green atoms represent the carbon, and these are arranged in a zigzag fashion with every carbon in the plane of the page. The hydrogen atoms are in white, and some of the hydrogen atoms, those at the beginning and the end of the molecule, are within the plane. However, you'll notice that some of the hydrogen atoms appear to be coming towards you, while some of the hydrogen atoms appear to be going away from you. Now, the ball and stick representation doesn't really give you a sense of the amount of space that a molecule takes up, such as hexane, but the next representation does. We call this a space-filling representation. And this can be useful for thinking about steric interactions. We'll encounter those more in Chapter 4.
The most commonly used way of depicting an organic molecule, however, is the skeletal bond line formula. Now, every carbon here is represented at the vertex of this zigzag line, and all of the hydrogens are omitted. We'll talk more about this later in this video. Finally, if you wanted to include the labels, but you wanted to condense how they might be connected together, we would use condensed structural formula. So this is hexane, and we read it from left to right. So CH3, CH2, 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 CH3. Now, obviously saying CH2 a number of times like that, it's a bit of a pain. We can condense that further to CH2, place it in brackets, and then place a 4 because there are 4 CH2 groups. So we're going to move on to the next slide now, where we consider how to represent three-dimensional bonds in 2 dimensions. So I alluded to on the previous slide the importance of understanding how to represent three-dimensional structures, and the best representation presented was the ball and stick model. However, drawing that would be a bit of a pain, and so we need a better way of doing this. Now, the image that I'm presenting to you is of children whose mothers took the drug thalidomide. And thalidomide in pregnant mothers was designed originally to prevent morning sickness. However, the 2 molecules that you see now have 2 different shapes. And these shapes can, in the body, be converted into one of these shapes that is particularly harmful and causes these birth defects. Now, you'll notice that these shapes are different in the sense that they have a solid wedge and a dashed wedged bond connecting one of the rings to the nitrogen atom. Now, what does this mean? Well, let's look at a simpler molecule. This is the skeletal formula of an alcohol. Now, the alcohol is the OH group, and on the ball and stick model, we can see that this is coming out towards us. And when a bond is coming out towards us, we use a solid wedge to indicate this. Now, the hydrogen technically should be left off of this skeletal formula, but I've included it so as you can see that the dashed wedge is what we would use if an atom is going away from us. So we're now going to think about, or just recap, some of the valences of different atoms and the types of bonds that they form. A quick reminder here that whenever you see something that's bonded to hydrogen, it's always going to have only one bond. When something is bonded to oxygen, there will be 2 bonds. Now, those bonds can be single bonds, as represented by the alcohol. They could be an ether, as represented in the second structure, or they could bond as a double bond, which is represented in the third structure. Okay, so when making bonds to nitrogen, nitrogen has to have 3 bonds. So you can see in the first structure that those 3 bonds can be single bonds, as indicated by the single line. In the second structure, the nitrogen can be bonded to using a double bond and a single bond, as indicated by the second structure. And in the third structure, when you have 3 bonds, then this can be connecting a carbon and a nitrogen together using a triple bond, as indicated by the 3 single lines. This is the antibiotic vancomycin, and as you can see, it has a particularly complicated structure. Now, if you imagine trying to draw the displayed formula for this, it would take quite a lot of time. The structural information about this, including where the atoms are in 3-dimensional space, is given to us in a 2-dimensional format. The stereo bonds, those are the wedged bonds, the solid wedge and the dashed wedge, indicate the position in 3-dimensional space of some of these atoms. Now, there are some hydrogen atoms on here, but notice how these are connected to the heteroatoms, oxygen and nitrogen. All of the carbon
in the carbon framework and the carbon-hydrogen bonds have been removed, we're going to learn how to draw skeletal formula in the next few slides. On this slide, we see a dashed formula with stereo bonds so as to get a sense of where these atoms are in three-dimensional space. Now, the first thing that you do when you're converting this to a skeletal formula is, if it is a non-hetero atom, that is, if it is bonded to carbon, we take away the hydrogens. Now, there is a carbon-carbon triple bond, and I want you to observe that this has a linear structure, and that already we're starting to form a zigzag. So this is the first step. The next thing to do is just to simply remove the carbon atoms. Now, notice how on the carbon-carbon triple bond that if you don't keep this as being linear, then you might accidentally introduce additional carbons. So you must make sure that you observe the molecular geometries of each of the atoms involved in bonding. This is a task that I would like you to complete now. So each of these structures represent the displayed formula for a number of different substances. What I would like you to do is to try and to construct the skeletal or bond line formula for each of these substances. So please pause the video and resume when you are ready. So here are the answers to that previous problem. Now you can see that in the first example, all we've done, and it's the same for all of the other examples, is to replace the carbon atoms with zigzag lines. The hydrogens, if there are any, will only be bonded to heteroatoms. In this sequence, we're going to discuss constitutional isomerism. But before that, let's have a little think about what isomers are. Now, isomers are compounds that have the same molecular formula, but different structures. Now, this branches off into two sections. The first is the one that we will be concerned with, and that is constitutional isomers. Now, these are different compounds that have the same molecular formula, but differ in the sequence in which their atoms are bonded. That is, their connectivity only. Now, on the right-hand side, we'll be focusing on stereoisomers in later lectures. However, you should be aware that these stereoisomers will involve the use of wedged bonds, which is why I've introduced these to you earlier on in our lecture series. If we consider the molecular formula C4H8O, the shared molecular formula of these three structures gives us no basis for any understanding concerning the differences between them. Each of these represents a constitutional isomer in that they have the same molecular formula, but they differ in the sequence in which their atoms are bonded. That is to say, their connectivity is different. If we consider the structure on the left and the middle structure, then we can immediately see how their physical properties are different. The chemical properties are also different because the structure on the left is an ether, whereas the structure on the right is a ketone, and these have different reactivities, so hence they have different properties. Similarly, the structure on the right also has different physical and chemical properties and contains an alkene and an alcohol. So what we're going to do on the next slide is we're going to consider some constitutional isomers of a hydrocarbon. On this slide are a number of constitutional isomers of the hydrocarbon C7H16. What I would like you to do is to match up the skeletal formula for all of the identical structures. Just to give you a bit of a clue, there are two structures at the end that will have unique structures. Please pause the video and continue when you are ready. The answers will be displayed in 5, 4, 3, 2, 1 seconds. Now that we have eliminated most, if not all, of the identical structures, the next task is to match up the skeletal and condensed structural formulas. So I'm going to ask you once again to pause the video, and when you're ready, resume. The answers will be displayed in 5, 4, 3, 2, 1 seconds.